Hi, everybody. Thank you, Stuart, for the introduction. And thank you so much for having me come and speak at the Girls in Electronics course. I'm really excited to share my journey and the kind of experiences I've had in this electronics field so that it gives a bit of an idea to the girls um, to see if that's something that they're interested in. And I'm really hoping that this talk is useful for them. Right. So without any further ado, let's jump straight into it. Right, so I'll start with a little introduction about myself. So my name is Sohini Dasgupta. I'm the principal design engineer at onsemi. So my interest in technology started quite early on. Um, and this was when I was actually in school. And the kind of PCs that we were still using are the ones that are shown on the slide, the IBM PC running DOS. Um, so this is I'm talking about like mid 80s, and there was not much access to video games, a lot of information, a lot of self-learn material. So I had to rely a lot on what the school was teaching me. And very early on, I developed this fascination for the history of computer architecture that they started with. This was when I was in year one. Um, and they started introducing coding, and I still remember my sister dragging me to a book fair, and over there I found this book on coding for kids, and then I picked up that book, and that kind of set off my journey into coding, because I used that as a mode to self-learn. um, so I don't think any of you all would have seen these kind of floppy disks. This is where we would store, it's a memory, we would store information. And this is what the basic code looked like. And we didn't have access to C++ until I grew a bit older. And then, yeah, I was just fascinated with coding, and I would consider myself pretty good at it. Um, then later on, I continued through my later years, having a love for computers and stuff. So during my bachelor's, I took up physics as my main subject for honors degree, together with mathematics, electronics, and computer science, because I wanted to keep my options open, and physics was one of my favorite subjects. So at the time, I just wanted to take this one subject and then have all the other alternatives available to me. After I finished my bachelor's degree, I came to the UK. I went to Newcastle University to pursue my master's in computer science. Um, when I was doing my dissertation at the end of my master's degree, I was lucky that that dissertation topic, actually my supervisor thought it could be a really good PhD research topic. So then I had no plans to do a PhD, but I was really interested in taking this idea forward. I was working on a mixed asynchronous and synchronous system, so partly clocked and partly unclocked systems. Um, and I did my PhD in that. While I was doing my PhD, I had very close association and collaboration with University of Manchester. Um, the computer science team was led by Professor Steve Ferber. Steve Ferber was basically instrumental in developing the first Acorn RISC machine, which is now known as ARM. And they also developed this BBC microcomputer system that became part of like every educational system. And it was extensively used in schools for educating the kids on programming languages and so on. So it was a really lovely process that I had at University of Manchester. I enjoyed working over there with Steve, with my supervisor Doug, and yeah, it kept me pretty firm on the ground that I definitely love electronics and I should be pursuing my career in it. Um, Having said that, through this process of PhD and my postdoc at Manchester University, there were very few women. Um, Sometimes, including me, there would be two women in the group. So sometimes I did question myself that, is this the right field for me? Um, and then I stuck on because every so often I would feel, oh, my personality doesn't seem to match with them. My ideas don't seem to match with theirs. But then when I started traveling around for the conferences, for workshops, I went to Nice, Grenoble, Tampere, Bologna, all these places I traveled, and I built my own community of women, very strong-minded and like-minded women like me. And we kept in touch. We bounced ideas when we were in our research. So then you actually along the way meet role models that keep you going. And I met such amazing women during my time doing research, and it every single time kind of like nailed my interest in electronics as I went on. So then after I finished my postdoc, I I decided that I wanted to venture into the industry, and the first company that I joined was NXP. Over there, I worked on power modules. So we were making power modules for computing, for automotive industry. And the project that I was involved in was making power modules for the Microsoft Surface tablet. And that was very challenging and very interesting. And once I finished my stint at NXP, I joined Imagination Technologies. Over there, I worked on developing CPUs for self-drive cars and various other products. But then our main client was Tesla. And at the time, they were developing the self-drive cars, and Mobileye bought our CPUs to integrate them into Tesla. So I worked in Imagination for about 4.5 years before moving to Satixfy, which is a satellite communication company. So they make satellites that are launched where you could actually switch between moving from covering different countries based on the commercial demand or any catastrophe that has happened in any part of the world. And it was heavily funded by the government. That was also a very interesting project that I was on. And I worked in Satixfy for 1.5 years. Now, currently, I'm working for onsemi. They make, apart from loads of other things, the part that I am involved in is the imaging sensors. So they make sensors for various products. So I will go through that in the next few slides. So now I'm going to talk a bit about the kind of products that the imaging sensor group at onsemi work on. So they provide solutions for advanced driver assistance systems and autonomous vehicles, including parking assist, the surround and rear view cameras for better visibility, lane departure warning for more safety, and more to ensure driver, passenger, and pedestrian safety. So there are loads of solutions that are given for, as I said, for greater visibility, eliminating blind zones when you're driving a car, or provide features such as automated cruise control. So there are these various products, sensors that actually help you achieve these. Right. We are also on Mars. We are proud to provide NASA CMOS image sensors for the entry, descent, and landing phases of the Persevere rover. So that was a very interesting project. We also have we work with healthcare. So we developed this sensor for the pill cam. It is a camera inside a capsule that captures images. So you swallow that camera, it goes click, click, click inside you, and it replaces painful procedures like colonoscopy. So it's basically making people's lives easier. So this project was also very fascinating. So now going on to what does the team look like at On Semiconductor. So we are divided into the digital team, the modeling and algorithms team, the analog team, and all of these teams are overseen by project managers. We also have the lab and the IT team that supports all of these teams. Now, none of these teams actually work insularly, so they all work with each other. So they're always talking with each other. It's a very collaborative project, and we all come together when we design a product. So what is my role in the team? So I'm in the digital team, and I'm a digital designer. And I am supported by a sensor architecture team, design verification team, the firmware team, and the physical implementation team. So what do digital designers do? So we start with an architecture spec, which is defined based on what the requirements are that are set out by, say, a client or a need that has come up. We have seen a space in the market. So the architecture team comes up with a pretty high level architecture. Now, this is where I come in. I take the architecture spec and then I give it a little lower level design to achieve the high level functionalities, basically deciding how to achieve these sets of functionalities. Now, again, this work is not done alone. We come together as a team, we brainstorm. It's a lot of teamwork. We come up with different ideas, how these architecture can be implemented. And then once the specification is written and reviewed, that's when we start coding. So we code in what is called RTL, which is the register transfer level. And once we have got the code ready, and we think that it meets the requirements, we do some initial testing just to make sure, like, just sanity test that everything seems to work okay. Then we hand it over to the verification team. Now, the verification team makes sure that every aspect of the design is foolproof. So make sure that everything is working by writing the tests, extensive tests to test corner cases. And then once the designers and the verification team are happy, we then move the design to the synthesis stage. At the synthesis stage, we actually, it gives us an indication what the power would look like, what the area would look like. Then the gates are actually replaced. What was written in the RTL in a coding language is actually replaced by proper gates. So then that gives you an idea of the power and area and the performance of the system. Now, again, this is not a one-way street. We keep going back and forth between the designers, the verification engineers, the synthesis engineers, so that at the end of this process, we have a power efficient, area efficient, high performing system. Once we are happy with this, we then give it out to the layout engineers, who then make sure that it is production quality. It does all the layout of what this whole the analog, the digital, and all this system put together would look like. Once the layout is done, it is actually sent to the fabrication plant, and then we get the silicon is made, and then the silicon is sent back to us. And then we again get back to the validation process. So in the validation process, what we do is that we create real life conditions real life situations and see whether our chip actually works and it is doing what we set out to do at the architecture stage. So to do that, we have these various lab setups that creates real life conditions. Like over here, it's creating rain. So we are simulating adverse weather conditions. We put lights, like strong lights, and once we have the strong lights, are we able to identify between different colors? If there are moving objects like this wheel over here, are we able to still read the lights that are blinking behind the wheel? So these are the things that the sensor identifies and make sure that, yes, we can correctly still identify the things that we need to identify. Like over here, we have the traffic lights, and there's a car simulated over here where the computer is sitting, and the cars go very fast, and then we check whether it can still identify between flickering lights, between the red and amber. Does it specifically be able to identify these different colors? So all this setup is done in the lab. I'll show a quick video. So the car is moving quite fast, and then we have to make sure that the sensor is able to identify all the reflections, all the different colors, and so on. Right, so that brings me to the end of my talk, and I hope that you all have found it interesting. I would love to take your questions and comments, but before I do that, I would like to introduce you to Eleftheria, who's a new summer intern at onsemi, and she would like to share some of her journey and experience that she has had so far with you all, and we really hope that you find it really interesting. Thank you so much.